You've likely all seen the news by now. NASA found a possible sign of life on Mars. These tiny spots, barely visible to the naked eye, are the biggest space news in over 50 years. If this really is a sign of life, it would be the most meaningful discovery in the history of humanity. But we've been burned by false alarms before, so have we really done it this time? I'm Alex McColgan and you're watching Astrum. Join me today as we dig into the details of what Perseverance found, why scientists are excited, and what it will take to prove we're not alone in the universe. In February of 2021, NASA's Perseverance rover, or Percy to his friends, touched down on an ancient Martian lake bed. The Jezero crater was once home to a large body of water, with rivers flowing in and out, carving deltas and carrying sediment. The soil is rich in clay minerals that can only form in the presence of water. Percy has been sent to hunt for ancient microbial life. If it's going to find them anywhere, the Jezero crater seems like a good bet. You see, ancient lakes often contain perchlorate, which can be metabolized by microbes. Astrobiologists on Earth study microbes like this in extreme environments to understand if life could survive in similar conditions on other planets. The rover's job is to look for these possible signs of life, identify and store the most interesting samples of Martian rock, and prepare them to be collected by another space mission for an eventual return to Earth. One day, in July 2024, while exploring the edges of the ancient Neretva Vallis River channel, Percy's cameras spotted something unusual. A rock from the Bright Angel Formation. Two of the rover's instruments, the Planetary Instrument for X-ray Lithochemistry, or PIXL, and the Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals, or SHERLOC for short, detected sedimentary rocks made of clay and silt. On Earth, these materials are excellent preservers of microbial life, so Percy took a closer look, and it saw something amazing. The rock, also known as Chayava Falls, was rich in organic compounds like carbon, phosphorus, and iron, arranged into rings. Affectionately named leopard spots and poppy seeds, the tiny spots span 200 micrometers to 1 millimeter in diameter. But it was enough to raise the blood pressure of astrobiologists everywhere. The light inner part of the leopard spot is chemically similar to the surrounding rock, but the dark outer rim is enriched with iron and phosphorus. It seems to be evidence of localized iron reduction. Percy also detected organic carbon-based compounds in the rock, and based on its texture and geochemical composition, we strongly suspect this rock was once in contact with water. Usually, when we see such a combination of organics, water, and iron reduction on Earth, it's interpreted as a sign of microbial life. Suddenly, NASA had something very unique on its hands. Could this mudstone rock hold the first alien biosignature ever found? At the center of this story are two very special minerals, vivianite and greigite. Vivianite is an iron phosphate. On Earth it forms near metal ores and river sediments, where microbes like Geobacter metabolize iron instead of oxygen. They take in iron 3 oxide and release iron 2 as a waste product. The energy given off by this reaction then powers their metabolism, a process known as chemosynthesis. When the expelled iron 2 reacts with the phosphate and the water in the environment, it forms vivianite. Greigite follows a similar story. Sulfate-reducing microorganisms on Earth break down sulfate into sulfide, which reacts with iron to make greigite. But let's be skeptics for a moment and rule out microbes for now. What else could have caused these reduction reactions? Well, one explanation could be very high temperatures. The sulfide needed to produce greigite could have come from volcanic gases leaking into groundwater. But that means the sulfide would have had to migrate from a hot volcanic system into a much cooler environment, and there's been no evidence for such volcanic or hydrothermal sources nearby. Another possibility is that sulfate in the rocks was reduced to sulfide through reactions with organic matter. But unless temperatures exceed 150 to 200 degrees Celsius, these reactions would be very slow and require a huge amount of energy, making them unlikely. And studies of the rocks around this area have shown no evidence of high temperatures. So there's no way the surrounding environment could have got hot enough to reduce sulfate and form greigite. Another possible explanation is acidity. Both iron 3 ions and sulfate ions dissolve much more readily in water under acidic conditions than they do under neutral conditions, making them much more prone to reduction through purely chemical reactions. If the water on Mars was more acidic than we anticipated, that could have caused the spots Percy saw. Perhaps these spots were just the result of chemical processes on an alien planet, nothing more. But then, Percy spotted this little green mineral. Nestled near the sample site, a small rock of olivine knocked the acidic water hypothesis on its head. Olivine is the fastest weathering silicate mineral. Unlike other silicone structures like silicon dioxide, for example, olivine doesn't have strong silicon-oxygen-silicon bonds. Instead, it's made up of negatively charged silicate ions held together by the electrostatic attraction with positively charged magnesium and iron ions. In acidic conditions, these are displaced by hydrogen ions, breaking olivine down into orthosilicic acid and magnesium ions in solution. The more acidic the environment, the more hydrogen ions there are, and the more aggressive the dissolution of olivine would be. So the very fact that it exists rules out the possibility of acidic conditions causing the strange spots. When studying signs of possible extraterrestrial life, Perseverance needed the best camera it could carry. Mission constraints make heavy, bulky gear impractical, and when I'm shooting space, I don't want anything too big or heavy either. I recently tried the Dwarf 3 Smart Telescope from Dwarf Lab, today's sponsor, and this compact device really impressed me. Whether you're a beginner or a seasoned stargazer, it's got you covered. For beginners, one-tap auto settings capture deep sky objects, the moon and the Milky Way in no time. Once I set it up, it oriented to the sky and automatically found stars and galaxies using its internal sky atlas. With live stacking, taking repeated exposures of the same target, it produced clear, detailed images in minutes. I was shocked with what I was able to capture. Advanced users get pro-level tools too, like astromosaics and multi-night stacking. I was even able to schedule sessions, so it worked while I slept, capturing these clear nights automatically. Built-in processing creates publication-ready images without extra software, a godsend for someone like me who wants to minimize faff. It's a truly portable, smart telescope that lets you capture amazing moments day and night. I loved trying it out. If you're a fan of space, scan the QR code or use the link below. Astronomy enthusiasts who enter the code Astrum5 at checkout get 5% off. Science is ultimately about falsification. It's not about proving a hypothesis true. Much more often, it's about proving a hypothesis false. Over time, and through a process of elimination, all roads seem to point to the same explanation. And if that explanation holds up against enough skepticism for long enough, it eventually becomes an accepted theory, testable, reliable, and widely accepted by the scientific community. In this paper, the Mars research team tried to prove that these minerals were not left behind by ancient alien life. They started with a null hypothesis and systematically investigated all the non-living explanations for what they found. But after months of study, they concluded they just couldn't do it. Now, saying we can't explain how this was done by something non-living is very different from saying this is a definitive sign of life. For one thing, all our speculation and contained excitement is based on what we know about biochemistry on Earth. And no matter how tempting it may be, we cannot allow ourselves to assume that just because something happens one way on Earth, it would happen the same way on Mars. Maybe it has a totally different biochemistry we know nothing about. NASA's being extra careful not to say too much too soon. After all, we've been wrong about potential biosignatures on Mars before. Back in 1976, the Viking lander tested Martian soil for life by squirting it with nutrients labeled with radioactive carbon-14. If microbes were present, they'd metabolize the nutrients into radioactive carbon dioxide we could detect. And to everyone's shock, that's exactly what happened. Excited scientists thought they had proof of alien life. But in 2008, NASA's Phoenix lander found Martian soil to be rich in perchlorate, a powerful oxidant that destroys organics and releases gas when heated. What looked like a biological reason was really just chemistry, a false positive. Still, Mars kept dangling hope. In 1996, a photo of meteorite ALH 84001 made headlines. The rock itself was over 4 billion years old, from a time when Mars had liquid water on its surface. Under the electron microscope, tiny structures emerged, resembling bacterial colonies. The world stood still. Researchers thought they were onto something big, so big that President Bill Clinton gave a formal announcement about the discovery. Sounds a lot like NASA's recent statement of Perseus' discovery, doesn't it? But in 2022, those squiggles were ruled non-biological, explained instead by a water-rock reaction called serpentinization, another false alarm. So is our recent finding in the Jezero crater another close call? Or is it proof that the third time really is the charm? There's only one way to find out. We have to bring the sample home for further testing. That's where the Mars Sample Return mission comes in. It's a complex mission, which requires sending 3 separate spacecraft to Mars. Percy has already completed phase 1. It's drilled into Chayava Falls and tucked away a precious core sample of the mudstone rock mission scientists named Sapphire Canyon. Phase 2 would be to send another spacecraft to land near Perseverance, collect those tubes, and launch them into orbit around Mars. The third and final craft would collect the samples from the orbiter and ferry them all the way back to Earth. It's a huge task, with an estimated price tag of $11 billion. The Mars Sample Return mission was first announced in 2022 as a joint collaboration between NASA and ESA. Since then, it has been fraught with financial struggles and uncertainties, delaying the project from 2033 to 2040, before ultimately being suspended indefinitely. This is despite the National Academy of Sciences Decadal Survey, a meeting of leading scientists who get together every 10 years to decide the future priorities for progress in STEM, naming the Mars Sample Return as the highest priority for NASA 2 decades in a row. And that was before we discovered this potential biosignature on our neighboring planet. All we can do is hope this puts political pressure on leaders to mobilize the necessary resources to pull it off. So if we ever do get the Sapphire Canyon sample back home, what kind of experiments might scientists run? There's a good chance that, among other things, they'll be looking for 2 key fingerprints of life. The first is chirality. Amino acids come in 2 mirror image versions, right-handed and left-handed, also known as D and L amino acids. On Earth, life overwhelmingly prefers the L version of things, while non-living materials show more of a 50-50 split. If the Martian sample shows a significant chiral preference, either right or left-handed, that could be a smoking gun. The second fingerprint is carbon isotopes. Carbon comes in a few different flavors, most commonly carbon-12 and carbon-13. Again, life prefers one over the other. The ratio of carbon-12 to carbon-13 in living things is much higher than in non-living things. If we see a similar pattern in the Sapphire Canyon sample, that could be another clue that its origin is biological. You see, you and I may often think of discoveries like these in quite a binary way. Either they're a sign of life, or they're not. But NASA has a much more nuanced take. They recently proposed the Confidence of Life Detection Scale, a framework for ordering how likely discoveries actually are to be signs of life, based on a set of criteria. It has 7 levels, ranging from "we found something that could be caused by life" all the way to "multiple teams have independently confirmed life more than once." NASA hasn't stated where the discovery in the Jezero crater falls, but I'd guess probably somewhere between levels 3 and 4. If the samples come back and independent labs around the world all confirm that what we are seeing really did come from a biological origin, that would push us up to a level 6. Level 7 might even require going back to Mars and finding the same evidence in a completely different location. So, when NASA says this discovery could be the clearest sign of life we've ever found on Mars, they don't mean to say it is clearly life. But the Mars sample return mission could finally reveal whether we've always been alone in the universe, or did we once have a cosmic neighbor? Even if our sample turns out to not be life, it's still an extraordinary discovery that will help us understand our own origins even better. See, we think Mars is like a time capsule of an early Earth. Unlike Earth, Mars doesn't have any continental drift or an active plate tectonic system. Its crust has been frozen in place for billions of years, preserved in a way Earth's crust could never be. The ancient landscapes on our planet have been erased through tectonics, erosion, oceans, and volcanism. So when we study Mars, we're not just asking whether it once carried life, we're also peering into a record of planetary conditions that resemble Earth at the dawn of biology. In that sense, Mars is a window into our own origins, offering clues to what Earth might have looked and felt like before life left its mark. But let's dream for a moment, shall we? What if the sample does turn out to be life? Well, most immediately, it would indicate that Mars was habitable far longer than we imagined, since the sample comes from relatively young sediment. But more importantly, we'd finally answer the question, can life exist on other planets? And in the same breath, open a Pandora's box of follow-ups. Did life on Earth start on Mars, or the other way round? Did a meteor from interstellar space seed life on both our planets? Or did it arise spontaneously twice? Where else could life exist in the universe? How common is it really? It would also have implications on the Drake equation, a probabilistic formula used to estimate the number of alien civilizations in our galaxy. The FL value here, which stands for the fraction of potentially habitable planets that go on to develop life, would jump from vanishingly small to closer to 1, since 2 out of 2 neighboring planets would then have or have had life at some point. An increase in this value causes the number of civilizations in the universe to shoot up. But crucially, this coefficient only changes if life on Earth and Mars rose independently. If we're related, the products of panspermia, that still represents just one biogenesis event, and the outcome of the equation remains unchanged. There's a concept known as the 0-1 infinity rule. In astrobiology, it represents the idea that life can only exist in 0, 1, or infinite places. We already know it's not 0. If it's just 1, then we're alone, a single spark in the dark. But if it's 2, Earth and Mars, then why not 5, 5,000, 5 million, or even infinite places in the universe? Suddenly, life isn't rare. We're not special anymore. And personally, I hope that if we ever discover life out there, it brings us closer together down here. Thanks for watching, and thanks to our crew of astronauts over at Patreon who help us make science knowledge freely available to everyone. Chasing the algorithm can be hit and miss sometimes, so your contributions help us keep making the content we love. And if you want to join the Patreon, there's never been a better time to get in on the party. Just sign up with the link in the description. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.